listening to the STEMxm podcast, highlighting women in the fields of science, technology, engineering and mathematics. And now, your host, Mel the Engineer.
Hello everyone, and thank you for joining me for episode 23 of the STEMxm podcast. I'm your host, Mel the Engineer, and we're embarking on some new career areas today. We just wrapped up a mini-series on water and wastewater careers. That was episodes 17 through 21. And so now I'm trying to pull together another several episodes in the area of climate change. So today will be the first in that series. Joining us is Dr. Joanna Haigh. Dr. Haigh has been co-director of the Grantham Institute at Imperial College since 2014. For the previous 5 years, she was head of the Department of Physics. And Joanna's scientific interests include radiative transfer in the atmosphere, climate modeling, radiative forcing of climate change, and the influence of solar irradiance variability on climate. She has been published widely on these topics in scientific literature, and she is past president of the Royal Meteorological Society. She is editor of Quarterly Journal of the Royal Meteorological Society and of the Journal of Atmospheric Sciences. She's a lead author on the Intergovernmental Panel on Climate Change, you may know better as the IPCC, and she's a fellow of the Royal Society, the Institute of Physics, the City and Guilds and the Royal Meteorological Society, and an honorary fellow of Somerville College, Oxford. So today, I'm thrilled to bring you a chat with Dr. Haigh on a career in atmospheric physics. Welcome to STEMxm, Dr. Joanna Haigh. How are you doing today?
I'm fine, thanks, Mel. Nice to hear you.
So I want to start from the beginning of your life. Can you tell us where you grew up?
I grew up in a sort of medium-sized town about 30 miles north of London. Not very exciting, but home counties we call it.
And when you were a child, did you have interest in science at that time, or did it develop later?
I think I always liked maths, and then as a sort of, when I got to what you call high school, I definitely developed an interest in science. But all the time I had an interest in the weather and meteorology. So that was the sort of background.
Oh, that's interesting. So why do you think that is? What drew you to meteorology?
I don't think I called it that. I called it weather. But
yeah.
But I like the outdoors. And I liked just watching the sky. And then when the science interest came in, I built myself a little, grossly inaccurate, but, weather station that did rain and wind and had my dad's Maxmin thermometer and that sort of thing.
So your parents, they encouraged your interest, I take it?
Absolutely. Parents are always very supportive of everything I did, which has been wonderful.
Were either of your parents scientists?
They were both in health service. So my dad was a doctor, a general practitioner, and my mum was a nurse.
Okay.
But she gave up work when she had children.
So you went to college and you had this interest. Did that immediately drive what you decided to study?
No, I went to college, to university to study physics. I think mainly because I was inspired by a fantastic physics teacher at school, and I also think that doing a sort of broader science rather than sort of specialising at an undergraduate level is probably a good idea, and that was the advice I was given. So I did a physics degree and learnt a lot, but wasn't incredibly inspired, I have to say. I mean, you've got to remember this is back in the 1970s, so the courses weren't nearly as interesting as they are nowadays. So at the end of that, I wasn't really quite sure what I wanted to do. While I was a student, I met my now husband, and he's a historian, and he wanted to go and look round archaeological sites in the Middle East and Turkey. So we spent 6 months working to earn some money, and then 6 months going around the Middle East and Turkey looking at archaeological sites, which he was doing almost as a professional, but I was just going along and enjoying it, learning a lot. But also saw lots of interesting weather. Huge thunderstorms and dust storms and fantastic sort of sunrises and sunsets. And it sort of reminded me of how much I was interested in the sky. And so when I came back, I enrolled on a master's course in meteorology.
Very nice. Okay, I want to go back to something you said just a moment ago. So this physics teacher that inspired you, do you remember something specific about that teacher or the class that really drew you in?
Well, the poor guy, he was the only male teacher. It was an all-girls school, and all the teachers were female as well, and he got drafted in to teach physics, which most of the girls hated, and also because he was a young man, and of course he just got joked at all the time, of course, by the silly girls. But he was an inspirational teacher, and so when he got especially into like a sixth form, a senior class, and he had kids in there that were really interested, he just had fantastic ideas of all sorts of experiments and interpretations and things that we hadn't had before. So he was inspiration to me.
Okay, thank you very much. So you made the decision to do a master's program after spending this time abroad with your husband. So how did you decide to go on to get your doctorate? Did you work between your master's and your doctorate?
No, I didn't, because when I was on the meteorology course, I realised that actually I really was enjoying it and I wanted to do more of it. And so I wanted to do some research. So I very luckily got a place to do a doctorate program in actually what was quite dry physics. But then, of course, it had an application. So I thought it was really interesting.
So tell us about that. What was that application?
So it was to do with radiation transfer in the atmosphere. And this radiation is electromagnetic radiation, so not ionizing radiation, but radiation from the sun and heat radiation, and essentially the background to all the energy that's driving the climate system. So I studied how the sun's radiation was absorbed and scattered in the atmosphere, and things like the greenhouse effect, and how the gases in the atmosphere trap the heat, and then how they heat the atmosphere, and then that causes winds, and you use models to then simulate what happens when you change the heating to change the winds and all that sort of thing.
Okay.
I was actually also at the same time, this is in the late 1970s, working on stratospheric ozone, looking at the change in radiation and ozone, and this is before the discovery of the ozone hole. So we were doing all sorts of chemistry of ozone, but completely unaware of the fact that there was this great big hole in ozone over the South Pole.
Oh, wow. Okay. So I've got lots of questions. Why don't we start there with that bit? So could you tell us more about that ozone research in really rudimentary terms? Okay, sorry. So ozone lives in the stratosphere, up there in the atmosphere, about, say, 15 kilometers up. And it's produced by ultraviolet radiation from the sun, which divides up the oxygen molecules and eventually creates ozone. And that's important for two reasons. One, it's protecting us at the Earth's surface, and indeed all plant and animal life, from the strong ultraviolet radiation. And secondly, it heats the atmosphere up. So you get this hot layer of atmosphere, which is called the stratosphere, sitting above the colder layer, which is the bit that we live in, which is a sort of stable layer. You'll all know that hot air rises. So if the hot air is above the cold air, it's quite a stable sort of situation. So that's why ozone is very important. Now, why we were studying it was for two reasons. Firstly, because we understood that the chlorine compounds that were being put into the atmosphere by various human activities, particularly from sort of refrigerants, had the potential to destroy the ozone. So that was one aspect. The other aspect was to do with increasing amounts of carbon dioxide. So you'll be aware that carbon dioxide is a greenhouse gas, and actually it's causing this global warming that we've been experiencing over the last few decades. But when you're up in the stratosphere, actually what it does is it
cools the atmosphere because it's emitting radiation, and the radiation gets to space, and so it's actually cooling the atmosphere where it is up there in the stratosphere. And I hope this is not getting too complicated, but when it makes the atmosphere colder, the reactions that are destroying the ozone go slower, so you get more ozone. So we had the chlorine destroying the ozone and the carbon dioxide increasing the ozone. And my project was to say, well, what happens when you put the both in together? And we had quite a nice result, which was actually that in that sense, the two together of equal magnitudes doesn't add up to zero because of nonlinear relationships to do with the reaction rates of the chemical reactions. So that was the basis of my PhD. So it was a combination of chemistry and radiation, and mainly in the stratosphere.
That's so interesting. Okay, so when you were doing this research, they already understood that the chlorine compounds like CFCs could destroy ozone, but they didn't know the hole was there, right? Is that what?
Yes, that's right. But the big missing link was the fact that we were doing reactions which were just between gases. So you have chlorine gas or whichever gas it is that's containing the chlorine up in the stratosphere reacting with ozone and other gases and depleting the ozone that way. What was actually happening in the ozone hole was more complicated, so that the thing that created the ozone hole was not this gas phase chemistry that I've just described, but actually chemistry sitting on clouds. So you've got very, very cold clouds up there in the Antarctic, and the particular chemistry it only works on surfaces. So it worked on the surfaces of the clouds, and that was far more effective at destroying the ozone than this gas phase chemistry that I was working on. So people only understood that was an issue sometime later.
That totally blows my mind. How did they figure this out?
Well, they discovered the ozone hole was discovered actually by two groups. One was from the British Antarctic Survey, which had been measuring ozone amounts from the ground using a very unsophisticated contraption, which consisted of a sort of wooden box and some mirrors and some detectors, just measuring the ultraviolet radiation coming in and deducing what the ozone must be. And they'd showed that in the Antarctic spring, the ozone had been getting less and less year on year for I can't remember, perhaps about 15 years or so. Also, a Japanese group had noticed that the ozone in the Antarctic was getting less from looking at satellite data. And they'd actually presented that at a conference, and I think sometime earlier, and I think everybody sort of thought, oh, they must have got it wrong or something. Anyway, so the British Antarctic Survey published this paper showing that there was this big ozone depletion, and then the Japanese data fitted in with that really clearly. So there was obviously a problem. So then it was identified that there was this big ozone depletion in the stratosphere. And of course, the next discussion is, oh, hang on, why is this coming about? Because it clearly wasn't to do with all this gas phase chemistry that everybody had been working on. So then there were a number of campaigns sending aircraft and other instruments, balloons and things to the Antarctic to actually measure all the chemicals and the temperatures and all the rest of it. And gradually the chemists worked out that it must be this chemistry on surfaces that I mentioned just now.
Okay, that's really cool. So from that place in your research, where did you go from there in terms of your work and your specialization?
So I've always worked on this radiation thing, but I've done lots of different applications. So I've looked at radiation measured by satellites and what it tells you about what's in the atmosphere below. Particularly, I've looked at properties of the ocean surface and of clouds. And then I've developed various sort of computer codes, which calculate radiative heating. So as I said before, if the sun's radiation is absorbed by the atmosphere, it gets heated up. But to calculate quite how much, you need to know the spectra of the radiation and also need to know the composition of the gases that are doing the absorbing. So that's one side of things. And the other side of things is on the heat radiation, which is essentially the greenhouse effect, where you get the hot surface of the Earth emitting heat radiation, and that's trapped and absorbed by greenhouse gases in the atmosphere. So again, we need to know quite what the composition of the atmosphere is, what its temperature structure is, to work out how much radiation is getting absorbed and how hot the atmosphere gets. So we have these two codes, one on the solar radiation and one on the heat radiation, and you create them that they work fast enough that you can then put them in climate models, which are these big models that are used to, well, forecast the weather as well as to study the climate.
Okay, so I want to ask a basic question. So how do scientists, how have they come to know that different types of gases create the greenhouse effect or create warming in our atmosphere?
So that's a lovely historical story. So right back in the times of Fourier, who's famous for his Fourier transforms, and I forget what date he is, 17 something, in France. He understood the physics of the greenhouse effect. He said that the surface of the Earth is warmer than it would be were there not an atmosphere there, because it's somehow trapping the heat radiation. And then after that we had John Tyndall in London doing experiments where he's actually putting essentially boxes of gases, different gases, and measuring how much infrared radiation were absorbed by these gases, so showing that there was the physical effect. And then I suppose the person who first really described the greenhouse effect of carbon dioxide as we know it today was Arrhenius, who's a Swedish chemist, Nobel Prize winner. And I think he was working in the 1920s, but I might have got that wrong. Might have been a bit earlier than that. And he actually did calculations that showed that if you got carbon dioxide in the atmosphere, it would heat the surface by a certain amount, which were fairly accurate, actually, surprisingly, given the lack of sort of spectral information that he had. And I've just sort of almost not exactly finished off the story, but I suppose the first person who really showed some evidence of global warming was a guy who's not very well recognised, called Guy Stewart Callendar. And he worked in London. His dad was the Callendar who was head of the physics department here at Imperial, where I work. And he was a very big and important person, and he was in the Royal Society and all the rest of it. His son was essentially a heat engineer, and because he's an engineer, he was considered to be sort of, of lower caliber or status or whatever in the scientific hierarchy. But he was doing all these calculations of radiation, and eventually he came to the conclusion that he'd got some records. I don't know where he got the records from, but of temperatures at various places across the globe over several decades. And he said that the temperatures are rising, and it was due to carbon dioxide concentrations, which were also rising. And I think he was the first person to actually draw that parallel. So he's an unsung hero.
Thank you so much for giving us that history. So I will be sure to look up each of these figures you mentioned, and I'll put
anything wrong.
Yeah, well, I'll put resources for them in the show notes so the listeners can see some additional information. You're listening to the STEMxm podcast. I'm Mel the engineer. And here on STEMxm, we aim to showcase the many careers in science, technology, engineering, and mathematics, while highlighting women and minorities who have succeeded in these fields. You can listen to this episode and all other episodes on iTunes, Stitcher, Google Play, or directly on the episode's show notes page at STEMxm.com. You can also sign up for our email list at STEMxm.com. And I want to thank you again, personally, for downloading and listening to STEMxm. So I just want to make it really clear for the listener. So in a laboratory, you can take gases that make up the environment and, maybe put them in some kind of vessel and run experiments and see how they react and get some idea of that effect that's happening.
That's right. So what you're doing is you're measuring their ability to absorb radiation. So if you shine some heat radiation on the gas and then you look out the other side and see what comes through, you can look at the difference and you can see how much has been absorbed. And it varies very strongly depending on the wavelength of the radiation. So clearly, when you've got visible radiation, it's composed of the rainbow colours going from red to blue, and then there's the ultraviolet on the shortwave side and the infrared on the longwave side. If you're looking at heat radiation, it's also got a spectrum, but that's at much longer wavelengths. But different gases absorb different wavelengths in that spectrum.
Okay, and so we hear primarily about carbon dioxide because I suppose volumetrically it's the byproduct that's produced the most from burning fossil fuels. But there's other gases that are also greenhouse gases that are more intense, so to speak. Could you just describe those a little bit and the influence of other gases, maybe like methane?
Sure. Well, I'll start off with water vapor because that's actually the strongest greenhouse gas.
Oh, yes, please. Thank you.
And if we hadn't got water vapor in the atmosphere, then the surface temperature of the Earth would be something like 30 degrees colder than it is. So we have water vapor to thank for the fact that we've got a nice habitable planet. So that's a perfectly natural effect, of course, and that's the sort of basis on which all the other gases are adding. So the next most important gas, as you say, is carbon dioxide. At current concentrations, it's probably having about something like a third to a half of the magnitude of the effect of water vapor in total. But of course, that's increasing year on year with the increasing concentrations of carbon dioxide. Then there's other greenhouse gases. So methane is an important one. That is on a per molecule basis, that's much stronger than carbon dioxide. But at the moment, there's less of it in the atmosphere than CO2, but also it's got a much shorter lifetime. So while methane lasts for perhaps about 8 years if you put it in the atmosphere, carbon dioxide lasts perhaps 200 years. So by all these means, carbon dioxide is actually currently having a bigger effect than methane on the greenhouse or human-induced greenhouse warming. There's also nitrous oxide, which is another one that comes largely from sort of agricultural practices. And then there's a lot of other smaller ones, including, in fact, the fluorocarbons that were also responsible for depleting the ozone layer.
Those chlorine compounds, those are also greenhouse gases?
Some of them, yeah.
Oh,
and in particular, actually, some of the gases that were put in, because when it was realised what was causing the ozone hole, there was the Montreal Protocol, which was an international agreement to stop emitting various chlorofluorocarbons into the atmosphere, to stop this effect. So they needed new compounds to replace those in the refrigerants and things. And the first ones that were proposed and started to be used were hydrofluorocarbons, and they're actually worse, or they have much stronger greenhouse effect. So they've just very recently themselves been banned. I think perhaps last year, 2015, 2016, they were actually banned. So, yeah. Do I need to say any more about that?
Well, so you brought up the Montreal Protocol, so I'd like to talk about that for just a moment then. So my understanding is that agreement, which was among multiple different countries, was sort of unprecedented. Like there hadn't been anything like this where we had come together with so many different groups and executed an agreement like this. So I wonder if you might give your thoughts on that and perhaps your opinion on why we haven't been able to achieve the same type of agreement and response with respect to climate change and reducing emissions of greenhouse gases.
So yes, you're right. I mean, the Montreal Protocol was a huge success, and the agreement that was achieved was remarkable in its international, everybody on the page, and subsequently acting on it too. And it's taken a long time, but the chlorine concentration has definitely been going down in the atmosphere, but we're just now really getting evidence that the ozone hole is beginning to get smaller. It's taking a long time because the chlorine compounds have very, very long lifetimes, so that takes a while for them to get sort of washed out of the atmosphere. So that the Montreal Protocol has had really a positive effect in negating the bad impacts of human pollution. So why haven't we done the same thing with CO2? Well, we are now, sort of. So at the Paris conference in December 2015 was the most remarkable agreement ever. It's called the Conference of the Parties of the United Nations Framework Convention on Climate Change, which is a very tedious name, but they have conferences every year to look at climate change. But they have a big one every 6 years or so. And the previous one to the Paris one was in Copenhagen in 2009, when there were hopes that some international agreement could be achieved, and it was a huge and terrible disappointment. Nothing was agreed, essentially, or a little bit, or something pathetic. It was, those of us working in climate science were just gobsmacked about how awful it was. So when it came to the Paris thing in 2015, we weren't going to get our hopes up too high, and the most remarkable thing happened. 197, I think, countries unanimously agreed to do something. And the United Nations has never had a unanimous agreement on anything, I don't think, before. So this was absolutely extraordinary. And not only that agreement, the whole thing has been ratified in less than a year, again, which is a United Nations record. So that is a hugely positive look at international agreement, or when we need to do something for the planet, we can all get together and agree to do it. So that is, of course, the positive side, agreeing that it needs to be done. The much more difficult thing, although it's more difficult, it's certainly as difficult, is doing it. So the countries have all committed to reducing their emissions of carbon dioxide or using fossil fuels by certain amounts over the next 10 and 20 years. And at the moment, the promises are not enough that we could reach a level of, as it were, less serious global warming. We're still on a trajectory to reach at least 3 degrees and rising in global temperature, probably nearer 4, which would have some severe effects. So we need the countries to not only live up to what they've promised, but also actually to do more. So as part of the whole framework agreement, all the countries are going to continuously revise their commitments, and there'll be a major stock take every 5 years to see, how we're doing. So that process has only just started, and we're all desperately hoping that it'll work.
So you said 3 to 4 degrees, and you mean Celsius, which means
oh yes,
more.
Sorry, yeah.
I just want to point that out. So that means a bigger change certainly than 3 to 4 degrees Fahrenheit.
Yeah.
I wonder if you.
By number 5.
Yeah, I wonder if you might speak briefly about the impacts, some of the impacts that that scientists would expect to see from that amount of change.
So everybody knows about global warming. So when we say 2 degrees, well, in fact the COP agreement said preferably less than 1.5 degrees, if at all possible. That's a sort of global average temperature, surface temperature change. And you say that to people, and they say, what, 1 or 2 degrees, that's nothing, it's warmer than that day and night, and certainly summer and winter, so what's the big deal? The big deal is that actually that has a huge shift on the whole climate system, and it means that there will be changes in weather and winds, and sea level, and ice cover, and all sorts of things that then has a knock-on effect. Furthermore, it's not equally, or it wouldn't be equally 2 degrees at all places on the globe. So there's some places that would feel it a lot worse, and other places that would feel it hardly at all. And of course, it also depends on where you live, on how you feel the impacts. So, for example, if there's sea level rise and you live in a low level island in the Indian Ocean, you're going to be submerged. So you actually no longer have anywhere to live if the temperature goes up by much above 1.5–2 degrees. So I mean, that impact is obviously very serious. There would be a few areas where they might actually benefit. So it's been mentioned that if you make the grain belts in Canada and the North and United States warmer, and in Russia, then perhaps it might be more productive in terms of producing more crops. So that there's that side of things too to consider. So it's a lot more complicated than just a sort of uniform global warming. Another factor that I haven't mentioned yet is that it seems pretty clear that as global warming progresses, it will also influence weather in a way that you'll get more extreme events. So what I mean by that is heavier rainstorms, stronger winds, bigger tornadoes, and all these sort of the extreme things will just get more extreme. So they clearly have a bigger local impact than you'd think about just from looking at large area averages.
Do you believe that we've already started to see this?
Yes, it's very, very difficult to look at these sort of local and extreme events. So we've certainly seen global warming. That's certainly a signal that's different from natural variability, and we can understand that very clearly. You can also see that just about in very large areas, particularly if you look over continents. So if you look over the whole of Asia, you can see that's the case, and some oceans too. If you look over the southern Atlantic Ocean, that's definitely warmer than it was. But if you're looking at whether or not particular extreme events, so if you've got a very strong hurricane or a very strong flash flood or something like that, can you say that that's due to climate change? It's a very difficult question, and it's something that's currently being researched a lot. But what's emerging is that the clever mathematicians and the statisticians are beginning to see that they can actually detect the likelihoods of these very extreme events occurring, and it's much more likely that they're occurring due to climate change than would just be the case under sort of natural variations. So we do think that as the climate warms and warms, these extreme events are likely to get more and more. I mean, it includes sort of things like heat waves. So there's been heat waves in France and in Russia over the last few years that have actually killed lots of old people. To what extent were those heat waves associated with global warming is quite difficult to identify, but you can understand very easily that if the average temperature is going up, then when you get a very hot year, it's going to be even hotter. So and then vulnerable people are going to suffer.
So I'd like to go back to your specialty for a moment. I have to admit that I didn't know that there was a discipline called atmospheric physics before I came across your profile. I kind of thought there was, atmospheric chemistry, and then there was meteorology. So
okay.
Could you just talk to us a little bit more about your discipline and maybe research that you've worked on over the years?
So atmospheric physics, the name says it all. It's the physics of the atmosphere, and it includes not only the sort of radiation things that I've been talking about, but also the physics of how clouds form and how they get moved around, how the winds blow. There's an awful lot of maths in there as understanding the flows in the atmosphere. And so when you're talking about meteorology, it includes a whole load of science, but the basic, the winds and the rain and the heating and all the rest of it is what we might call atmospheric physics. So I've been working mainly on the radiation side of things, so the solar radiation and the heat radiation, in a number of different ways. But over the past few years, what I've been focusing on is looking to see how changes in the sun might affect the climate. And that's it's interesting to me anyway, from several perspectives. Firstly, it's using the skills that I've learned over the years in radiative transfer applied to a particular situation. So if the sun's radiation were changing, and in particular if the sun's spectrum is changing, so you get more ultraviolet or less ultraviolet, what does that actually mean for the atmosphere? So I think it's a very interesting physics problem. But the other important aspect is that when you're talking about climate change, you need to make sure that when you deduce that, say, global warming is due to man-made greenhouse gases, you need to be quite sure that it's not due to something else that's natural. And one of the natural things could be the sun. So we need to make sure that we understand how much the sun is changing, whether its energy output is changing, and how much that could be affecting the climate, in order to be sure that we're right when we say that actually recent warming is due to greenhouse gases. Do you want any more on that?
Yeah, definitely.
This is the STEMxm podcast with Mel the engineer.
Any more on that?
Yeah, definitely. So do scientists expect the sun's radiation to change?
So this has been a question for research for many, many years. So there's been observations of solar activity. So in particular, you might be aware that there's sunspots, little black spots that sit on the sun, and they come and go fairly regularly in a sort of 11-year cycle. So there's more and then less and then more every 11 years. And this has been observed for a very long time. The ancient Chinese used to notice that there were sunspots and make notes of them. And there's been very serious records kept of sunspot numbers for at least more than 200 years in the Paris Observatory. So we know that there's this 11-year cycle, but we also know that the overall number comes and goes. So some periods, there's very, very few for decades. And then in other periods, you have the 11-year cycle has a much bigger amplitude. So there's been a question as to whether or not, solar activity, however you measure it, could affect the climate for a long time. Now, it's all very well talking about sunspots, and you can see little black spots on the sun, but it's not at all clear how that might affect the climate. You need some actual physics to go on to do the business. So the obvious thing is that the sunspots are somehow associated with changes in the sun's energy output. And people have been trying to measure the sun's energy output since they've had, scientific instruments that could measure radiation and temperature. So back in the 1930s, there were very serious efforts, I think, in the United States, in the Rocky Mountains, up in the very clear air, using ground instruments based on the ground, measuring the sun's radiation and very carefully recording that for years and years and seeing if it changed. And despite those very careful efforts, there was no obvious correlation between the changes in the radiation that they were measuring and, say, the number of sunspots. In fact, I think what those scientists were expecting was to see that when there were more sunspots, there would be less radiation, because you'd think a black spot would make the sun darker, so there'd be less light coming out. Perfectly reasonable hypothesis. But they weren't able to show that one way or the other. And it's only since the late 1970s, when we've actually had satellites sitting outside of the Earth's atmosphere, able to measure the sun's radiation, that have clearly been able to show that it does vary. So the problems with the instruments on the ground was, even though that they were in a very, very clean atmosphere and high up a mountain, the effect of the atmosphere above was still too much it blotted out the sort of the signal that was coming from the sun. But when you're outside of the atmosphere, you can measure this much more carefully. So the radiometers sitting on the satellites have shown very clearly that when there's more sunspots, there's also more radiation coming out of the sun. And it's quite a small amount. It's only like a bit more than 0.1% of the solar output, variation from maximum to minimum on an 11-year cycle. So it's a sort of relatively small amount. But in terms of global warming, it's not a negligible amount. So we need to understand how those variations might be heating up or cooling down the climate below, and take those into account when we're looking at climate change. So I mentioned that the sunspots come and go on the 11-year cycles, but there's sort of longer term variations. And back at the end of the 17th century, there was a period when there was very, very few sunspots observed at all for decades. And it wasn't just because people weren't looking, or they really were looking. They'd seen them before that period and they knew they should be there, but they just couldn't see them. So this has become known as the Maunder minimum, low solar activity period. And it was noticed by various people that sort of happened to coincide with a period that had become known as the Little Ice Age in climate. So there's clearly an assumption or a suggestion that the lower solar activity was associated with the cooler climate, and that's been a question that's been recurring, well, for a long time. In fact, the Victorians knew about the lower sunspots and the colder climate, and there was a whole activity in the Victorian scientists. It was called sunspottery, and they were treated as sort of as idiots and quacks. And we could go into that in great detail, but it's got a long history. Now we do know that there are changes in the sun, that there probably was less solar radiation coming out during the Maunder minimum, but two things about that. One is the amount of radiation difference is very small, and could only have a very small effect on global climate. Secondly, the thing that was called the Little Ice Age was actually not a global phenomenon at all, but just really part of a cooler period in northwest Europe. So you'd think that if it was to do with the sun, it would affect all parts of the globe, and it didn't seem to be affecting all parts of the globe. So that the whole science sort of went through a period of completely dismissing that idea and saying the sun's not doing anything, and we can forget about it. Now we're getting into another very interesting scientific period where we're beginning to understand that it's not just the changes in the sun's total radiation that's having the effect, it's the changes in the ultraviolet, and that's what I've been studying. And furthermore, that when it changes the ultraviolet, it's not just a global effect, but it has regional effects. And one of the effects where it might be seen is in Northern Europe. So there's now a sort of new attempt to try and study how changes in the sun's ultraviolet radiation might produce regional changes in climate. And it's really exciting science, and as I say, it's something that people are working on now. It doesn't take away from the fact, however, that changes in solar activity are definitely not causing global warming as a sort of big effect.
So for your research, you mentioned earlier that that you're able to use satellites to look at impacts of radiation in the Earth's atmosphere and on the surface. Could you tell us more about that? Tell us about these instruments and what they pick up on, and then what you and your colleagues can discern from that.
Yes, I mentioned earlier that the satellites have been very helpful in measuring solar radiation, but they have been enormously helpful for weather forecasts and climate studies. So the satellites sitting outside the atmosphere can look downwards into the atmosphere and measure the radiation coming out. And by very carefully discerning the wavelength composition, the spectrum of that radiation, they can deduce the temperature of the atmosphere as a function of height. So they can measure the temperature from the surface up through the atmosphere, which is extraordinarily useful if you want to put it into a weather forecasting model. And clearly they're orbiting the Earth every 90 minutes, and they cover the Earth twice a day. So you've got this repeated measuring over the whole of the globe of the temperature as a function of height.
So it's a 3D depiction of...
Exactly.
Oh, that's amazing.
It is amazing. And so they feed these data from the satellites every 12 hours into the big weather forecasting models, so that the models are sort of kept on track. So, of course, if you've got a big computer model, it's not perfect, and it can sort of, if you leave it running for long enough, it can sort of deviate off into a sort of non-real world scenario. But actually, I've got to say something about that more in a minute, because that wasn't a very good statement. Yeah. If you've got a weather forecasting model, it can go a bit wrong, but by continuously engaging with these data that are coming from the satellites, you can sort of keep it on track. So it can do the forecast for the next hour or the next 6 hours of the local weather, but then you get the new satellite data in to just make sure that its temperatures are not doing anything really bad. I was correcting myself there, because I was beginning to realise that what I was saying might suggest that you couldn't do climate modelling, because you can predict the weather sort of up to 10 days ahead. So and after that it goes bananas. How can you possibly predict the climate, 50 to 100 years ahead?
Sure, and maybe that's something worth addressing too. I think that's a very common, at least in the U.S., misunderstanding that climate is not weather.
Yeah. Shall I have a go at that one now?
Yeah, absolutely.
So when we're interested in weather forecasts, we want to know, what the weather's doing in a particular place, a particular town, over the next few hours or the next few days. So it's a sort of short time scale and very local effect. And we want to know, how much the rain's going to be and what's the temperature and the cloudiness and all the rest of it. When we're looking at climate change, we're not looking at a particular town at a particular hour. So we might... however, look at a particular region, so perhaps the whole of the UK, and perhaps at a particular, averaged over a year or even several years into the future. So we're not looking at the particulars of the weather, we're looking at the sort of average weather. And that you can't predict, what's going to happen to the particular weather in London in 2021, February the 3rd or something, but you can say that in 2021, the weather or the climate in the UK is likely to be so much warmer than it is today. So there's a sort of a range of values around your forecast, which you couldn't be precise within that range, which is representing climate uncertainty. But as you increase the amount of greenhouse gases in the atmosphere, this whole range moves upwards. So it's got a breadth, but also the mid value is moving upwards. And the weather is going on inside that range, wiggling around inside the range, but the net effect is an envelope moving upwards. Does that make any sense?
Yes, that makes sense. But I wonder if you could explain for us how we can tell that these like envelopes that you just mentioned are there and where they're going.
That's right. So when we're looking to the future, we predict the future. We don't know the precise values, but we can say that it's in a range. So we might say that the global temperature is going to go up by, say, 2 degrees, but it might be somewhere between 1 degree and 3 degrees. So there's a range of uncertainty. So when we're looking at the weather, it's changing enormously on a day-to-day basis, and clearly on a year-to-year basis as well. It's not, warmer one year than the next precisely. But if you look within this climate range of uncertainty, as we go forward, the weather is changing within that range, but the overall range is moving up with global warming.
So in your professional life, do you feel fulfilled by your career, and what is it that maybe you like most about your work and your research?
I feel hugely privileged to have had the career that I've had, because I actually love the science and I just find it intrinsically interesting all the time, but also because it's sort of relevant to the real world, and you can talk to people about it and they sort of perhaps have an opinion or an understanding of what you're trying to is reinforcing. Another nice part of my job is that I interact with students, with young people all the time, and they're a huge source of inspiration and enthusiasm and laughter too. So I love that aspect. There's some aspects that I haven't enjoyed quite so much, which is, of course, you can imagine, the sort of paperwork, the form filling, the reports and all the rest of it. But, hey, there has to be some downside.
Right. Do you have any thoughts for young women who are looking to go into the sciences and maybe advice for them?
I say go for it, but don't be told what to do. Obviously, take advice from people and listen to what people say, but don't be told what to do, because you know for yourself what will really suit you and what won't. And I think that's sort of pretty good advice for life in general. I mean, when you have babies, don't be told by people how you should or shouldn't be looking after them. Just listen to advice, but do what you know and your gut instinct is correct. And then you need some friends, supportive friends, partners or whatever, that you can cry on their shoulder when you need to. And in that way you muddle along.
That's great. That's really good life advice. Dr. Haigh, it's been a real pleasure. Thank you so much for taking the time to speak with us today.
You're welcome, Mel. Bye-bye.
All right, bye-bye. Thank you again for joining us for episode 23 of the STEMxm podcast with Dr. Joanna Haigh. You could probably tell that we ran out of time, and I was trying to squeeze in as many questions as possible before she had a meeting with some of her students. But I really enjoyed this particular episode because I learned so much. What a fascinating specialty area of physics. You can find this episode's show notes at the usual place, STEMxm.com/episode 23. That's STEMxm.com/episode and then the number 23. Stay tuned for our next show, where we'll be chatting with another scientist who specializes in the impact of climate change and sediments on coral reef systems. So we'll be going from up in the sky to down in the ocean for episode 24. If you have any questions, or if you'd like to hear about a certain STEM career that we haven't covered already, please feel welcome to reach out to me through the website, on Twitter, where my handle is STEMxm Podcast, or on Facebook or Instagram. You can find those pages at facebook.com/STEMxm or instagram.com/STEMxm. Thank you again for downloading and listening, and I'll catch you in episode 24. Bye, guys.
This has been an episode of the STEMxm podcast. Thank you for listening. We would really love if you could pop over to iTunes and give us an honest, positive rating. It helps more listeners find us to learn about STEM careers. Thanks again, cheers, and we'll catch you on the next episode.